the function used by the kernel to display files to the user. So when the user types the command ls or uses the finder, for instance, to enter a directory and browse the contents of a directory, he will invoke the function getDirEntries, which is basically a small kernel function that looks to the file and looks to the file tree and returns a list of files in that directory. In our case, we would like to modify that list of files, and we do this by intercepting the function getDirEntries, let the original function run, take the data back, parses through the data, find the entries that we want to remove these entries from the data, and then return the end result to the user. So in this case, the original syscall, which in this case here is open, the original execution flow would be that it looks up the syscall open in the syscall entry table and then invokes that function. In our case, we want to divert this call flow. We want to change the sysentry struct table so that it points to our own function, and when we actually run this function, we're going to invoke the original open function if we want to, or we can just end it there or say the file does not exist, or in the case of open, we could, for instance, open a different file. Opening a different file comes in handy if we want to replace a file in the file system. Let's say that we want to, as an example, we could say that we want to switch out the SSH binary. We want to have an SSH binary that logs usernames and passwords used by users in the system, but we don't want Tripwire, the integrity monitoring software, to actually detect that we have changed the binary. So we're going to modify the open call so that if you open the file in execution mode, it opens our new binary. But if you open it in read mode, as Tripwire, for instance, would do, you give it the original file. And then you hide the new file using, by changing the characteristics of getDirEntries. So in this case, what we would do is that we would subvert the sysentry table, call our new function, and in that function, we would call the original open call and change the output or change the path. But the sysentry table just basically contains a list of system call functions and their address in kernel space. So let's go back here. So the syscall entry table contains a large list of function pointers. Each function pointer contains a number of properties, for instance, the number of arguments, flags, the implementation function, which is pointed to the actual function. The problem for us here is that we need to find it where it is in kernel space. Landon Fuller actually developed a really nice way of doing this for kernel extensions. When Mac OS X was at, I think it was like version 10.3, Nemo released his WeaponX kernel rootkit. This rootkit basically mirrored how Knark worked for the Linux platform, in that it just simply replaced certain functions in the sysentry tables, and Apple responded to this by removing that table from the exported symbols of the kernel. That means that we cannot simply reference the sysentry table in our code when we develop using Xcode, for instance. So if we develop something using Xcode, if we reference the sysentry table, as its name, just sysent, it will simply say unknown. It doesn't know what it is and how to use it. But there is something else that we can use, and that is called something the nsysent. And that is basically a variable containing the number of available syscalls. This variable just happens to be stored next to the sysentry table in the kernel space. So Landon Fuller developed this very, very short routine that basically finds the nsys variable and then returns that value plus 32. So if you're on the x86 platform, it's plus 32 for unknown reason, probably something that has to do with compiler alignment. And if you're on your PowerPC platform, it's just next to it. So this way we can find the sysentry table even though it's not exported from the kernel. Now, doing this in user space is basically the same thing. We don't have the kernel extension where we can just reference an object like nsysent, but we have access to the actual kernel. It's in /mark kernel. And it contains the nsysent symbol, which can be resolved just as we does inside a kernel extension. And as I said before, it's just 32 bytes away. I think there was a beautiful example, but there wasn't. So, the kernel image is just a normal binary, or Mach-O binary, containing two architectures, i3xx and PPC. And Bosse actually developed this really nice little library that you can use to resolve kernel functions. It's called the libs2a, and in this small example here, it basically just says resolve the nsysent function and add 4 if it's on a PowerPC, or add 28 if it's on the add an additional 28 if it's on a PowerPC platform, on the x86 platform. So we've actually located the sysentry table. We can read, we can write, and we can allocate space. What are we going to do? Brings us back to this slide, which I basically already talked about. But what we want to do in the case of open or get dirent, for instance, is that we want to subvert the normal execution flow of this function, and we want to replace it. Now, if we do this using a kernel extension, we can compile our own C code and load it into the kernel, and the compiler and the loader will assemble and link our own our code. If we do this using raw reads and writes to the kernel, it will not assemble. It will assemble it, but it will not link it for us. So we would have to have assembler code that we basically introduce, or binary code that we introduce into the kernel. But the concepts are virtually the same. So, Bosse developed this really nice proof of concept rootkit that uses these techniques. I'm afraid that I will not be able to run his really fancy demos, but it uses this technique to hook the read and I think it's get dirent and something else. You can look it up. He has it available on the web, and you can try it out. So I'm just going to skip the demo part here. So I'm going to talk a bit about rootkit detection, because this is also interesting. Can we actually detect if we've been infected? Is there some way for us to know if we've